So in the last class, we discussed on different classification of states, and today we discuss on the classification of the whole chain. So this is the idea. This first classify the all state, different individual state, and then classify the whole Markov chain. Like we first classify the student of a school. Say this student is bad, this student is good, this student is say average. Then we classify the whole school. So the school is good if this 90% students are good, something like that. School is bad if the 80% students are bad. So first classify the individual element, then classify, then up on the basis of that we classify the whole Markov chain. Now we classify this like a closed set. We also classify some subset of the state also. So we classify the states, classify the whole chain. We will classify the whole chain, and we also classify the individual state. So the closed set, we know what is closed set. Closed set of the state is just a non-empty set. You just briefly recall the last video we just do up to this. So in the non-empty set, S of state set, so is a subset of state space, is called to be closed. It's said to be closed if no state inside this C. So no state, say C is, say X is a state, and this belongs to C, where belongs to C, leads to any state, outside C. So it is just outside C. That means if if Y not in C, then X cannot lead to Y. So X not leads to Y. Doesn't lead to Y. From X, the probability of going to Y is 0. Just that means what is this? That means the probability of Xn is equal to Y, given that is X0 is X. This is 0 for all n. This is 0 for all n. So then we call for every X inside the closed set and every Y outside this. So that means it is rho xy. Rho xy is 0 for all X in a C and all Y in not in C. So the last class we do up to this, and just simple note is that if C is closed, then a Markov chain starting at C, starting in C, that means it's starting at any element of C. That is the initial distribution, the spectrum of the initial distribution, the subset of C, will with probability 1 stay inside. So say it's inside C for all time. So this is just a story. You can just say in your just language, but this is not the mathematical language. What is the meaning of that? The meaning is that rho of xy is 0. So this is the mathematical thing. So rho of xy is 0. But the story is this. So if you start from here, you never go outside this. For all time you are in there. So that means for any state from that to the transition probability to go from X to Y, the outside is 0. Now obviously that if A is an absorbing state, then this is closed. Obviously. So absorbing means it's the probability of A to A is just 1. Otherwise it is 0. So this set is absorbing state is closed, and obviously the union of closed set is closed. So this union of closed set is closed. Now some definition again to classify the whole chain. So the definitions are: If A is a closed set, so a closed set C is a closed set. A closed set C, not A, the C is a closed set, is called irreducible. So irreducible is called irreducible if X leads to Y for all xy in C. What is the meaning of that? So that means from if you start in this irreducible closed set, then you can't go outside that, and you will go everywhere in that set. That means irreducible, something like that. So if say A is the absorbing state, B is the absorbing state, so set containing AB is also a closed set. Set containing A is a closed set. Set containing B is a closed set. Set containing AB is also a closed set, but set containing AB is not irreducible because you can't go from A to B. So that is like an atom or reducibility. You can't further decompose this closed set to a closed set which is a subset, proper subset, and again a closed. You can't do this. So this is a minimal thing. So from after that you can't drop any element. If you drop an element, that can't be a closed set. So minimality condition is there. So this is called closed set, which is irreducible. So union of two irreducible closed set is not a irreducible. It's a closed set but not irreducible. So this is one important thing. Now the interesting thing is, if C is an irreducible closed set, then either every state in C is recurrent, or you can easily guess that every state in C is transient. So this is the interesting thing. So in irreducible chain, irreducible set, closed set, this every element is either transient or every element is recurrent. Why this is so? The idea is basically this, that this is not a mathematical proof. The idea is if you start with somewhere in X, if it is a recurrent, that means it goes to the least to the Y with positive polarity, it should go to Y. And once you go to the Y, again it should come to the X because X is recurrent. Recurrent means is come infinitely many times in the X. So once it's again visiting the X, and with again positive polarity, it will go to the Y. So that means if it's infinitely times it is visit X, that means it also infinitely visit Y also. If you start from Y, you should go to the X because it is just irreducible. And since X is recurrent, it visit infinitely many times for X, and so Y also infinitely many times visit Y. And if one state is transient, then can't be any other single state is recurrent. If one state is transient, so can't be a mix up of transient and recurrent. So if there is a recurrent, then all are recurrent. So it can't be so that some are transient and some are recurrent. So either all are transient. If at least one of them is recurrent, then all are recurrent. Now it is true for irreducible closed set, but if it is a closed set, just say there are two closed set, an union of that two closed irreducible closed set, and take the union, and that set is a closed set. But this is not may not be this property hold, because the say C1 is a closed irreducible closed set of all transient state. C2 is another set of irreducible closed set, which is set of all recurrent set. Now the union is closed, but is not irreducible, and some are recurrent, some are transient. Because if from recurrent you can't go to the transient state, and from transient state you can't go to the recurrent state, because for the closure property, that's closed because they are closed. So this is the basic idea. So you need a mathematical rigorous proof. Before that, we just take one more thing. If let C be an irreducible closed set of recurrent state. Now, if the set of all the closed set are all are recurrent, either it's all are recurrent or all are transient. So consider the case where the all state are recurrent states. Then what happens? Then rho xy is 1. Obviously, rho xy is 1, and this probability that is number of time visit, infinite number of time visit is also 1. Start from x is visit y infinitely many times is also x, and this mean time is this mean is infinity. Now this is true for all x and y in C. So if it is irreducible closed set and all the states are recurrent. Now we classify the chain. We define one more term. So next definition is an irreducible Markov chain is a chain. Chain means it is a stochastic force, is also called chain, whose, if it is countable, just number of x1, x2, xn, or sequence of the random is also called chain. So chain whose state space is irreducible, state space are irreducible, that is a chain in which every, so since it's irreducible, so it's a one state is irreducible, that means every irreducible Markov chain means it is a the chain is whose state space is irreducible. So that means what is this? So state space is irreducible, the whole state space is irreducible. That means you can't further decompose this. So every state, from every state you lead to every other state. So that means a chain in which every state leads back to itself and also to every other state. So starting from x, so the whole state space is irreducible. So if you're starting from x, you visit infinitely many times that x, and you visit infinitely many times that y. It leads back to itself. So this is the definition, and some obvious result are this: an irreducible Markov chain. An irreducible Markov chain is either a transient chain. So because it is irreducible, if it is a one state is transient, every state is transient. And if one state is recurrent, either all the state is recurrent or all the state are transient. So it's either it is transient chain or it's recurrent chain. So you can't mix up two state. Recurrent chain. So either is recurring or is a transient. So one more thing is this: an irreducible recurrent chain. Irreducible recurrent chain recurring Markov chain. So it's the irreducible recurrent Markov chain. Visit every state infinitely many often. Visits every state infinitely often. So infinitely many times. So it is also called infinitely often, infinitely many times with probability 1. With probability 1. So to start from anywhere, this is a recurrent Markov chain is visit everywhere. So because all the states are recurrent and it is closed. So go from you should go from one. It's irreducible. So not the closed property is important. The important is since it is irreducible, starting from x, and x is recurrent, y is also recurrent, and starting from x you should go to the y because it is irreducible. Otherwise, it may so happen that one particular subset is recurrent, and say like I say set of all absorbing state. every state are absorbed, then it is not irreducible basically. It's a closed, it's a recurrent state, a recurrent chain. Every state is recurrent. But it is not a, since it is not a irreducible, it can't go from one to another. If you start from X, it's just always there. It can't go to Y. Now, if it is a recurrent and irreducible both, then it start from X, you go to the every state infinitely many times. Because X leads to Y for every Y and for every X with probability 1. So this is an interesting thing. And one more thing is, if C be a finite irreducible closed set, since it is finite, so can be so that every state visit finitely many times. So at least one state must visit infinitely many times. So it is a finite irreducible closed set of states. So is at least there is at least one state which visit infinitely many times. But since it is irreducible, from that state you can go to the every state with positive probability. That means the other state also visit infinitely many times. Every state, then every state in C is recurrent. So this is the basic idea. So we need a formal mathematical proof of that, but this is a intuitive overhead or high level concept, high level thing. So this is not a mathematical. This is a high level. This is also called high level concept, high level thoughts, and you have to go to the deeper mathematical notation to prove all these things. But intuitively it is clear. So the statement, but needs to prove all these things in say clear mathematical formulation or computation. Some example. So is a important example. So consider the Markov chain. Consider a Markov chain having the following transition matrix. The following transition matrix. So what is this matrix? Is say this state is 1, 0, 1, 2, 3, 4, and 5. So it's a big one. 0, 1, 2, 3, 4, and then 5. So it's a bigger one. And now this is 1, 0, 0. From 0 to 0 is 1. So it is absorbing state. 0. Every row sum must be 1. Column sum may not be 1. 1 by 4, half 1 by 4. So already 1 is there. So 0, 0. Then 0, 1 by 5, 2 by 5, 1 by 5, 0, 1 by 5. From 3, it is just 0, 0. This block is 0. This block is 0. Now this is 1 by 6, 1 by 3, half, and from 4 it is half, 0, half, and 5 it is 1 by 4, 0, 3 by 4. So this is the Markov chain. You can easily draw the graph of this Markov chain, the transition matrix, and now how do you know which one is recurrent or which state is transient, and what are the closed sets and what are the all irreducible closed sets? So if you can find the all irreducible closed set, that's the union is just the all closed sets. So if A1, A2, A3 is the only irreducible closed set, that means the closed sets are A1, A2, A3, and A1 union A2, A1 union A3, A1 union A2 union A3, and A1 union A2 union A3, and obviously the whole set, whole S is a closed set. Now, the idea is this: you just first construct a matrix. Construct a matrix with entries plus or on and 0, plus and 0. according as. So what do you mean by plus and 0? Is just according as rho xy is positive or 0. So it can be negative because it is a positive. So positive, if it is a positive, you put plus. If it is 0, we put 0. That is according as x does not, does or does not leads to y. So if x leads to y, we say put positive. Doesn't lead to y, we put 0. Now note that, so transition probability from x to y is positive. What is the meaning? This rho xy is positive. But the converse is not true. So transition probability is 0, maybe rho xy positive. So converse is not true. So rho xy 0 means transition matrix. If rho xy is 0, sorry, the converse is if rho xy is 0, then this transition thing is the transition matrix probability is 0. That is not true. But the converse is not true. But converse is not true. What is the converse? Converse is if rho xy is positive, then transition probability is also positive. That is not true. So if rho x is positive, then transition probability may be 0, because from x to y the probability is 0, but say x to z is not 0, it's positive, and z to y is positive. So from x to y is positive, transition probability is 0, but it's a one step. So one step transition probability may be 0, but the two step maybe there is positive probability. So that's why rho xy is positive. That's why the converse is not true. Now what is transition from 2 to 0? 2 to 0 is 0. 2 to 0. But p square 2 to 0. So p square means the two-step transition. This is actually, you start from 2 and go to the 1. Go to the 1 and then 1 to is go to the 0. So is that equal? It start from 2 to 1 and 1 to 0. If you start go 2 to 2, two step is not there. So if 2 to 3, from 3 it can't go to the 0. 2 to 5 also is the only thing, and this is positive. So transition probability may be positive 0, but the two-step transition may be positive. Now that's why this rho 2 0 is positive. It's not rho 20, it is rho 2 0, like rho xy. So what will be the next, the matrix? The matrix you can construct like that. So if it is a positive is there, then the matrix is positive. But this, if it is 0, then still the in matrix it may be positive. So 1 2 2 3 4 5. Now from 0 to 0 it is positive. So from 0 to anywhere is 0, because 0 is the absorbing state. So from 1 to 0 it is positive. 1 to 1 it is 0, but still it is positive, because 1 to 1 transition probability is 0, but you can go from 1 to 2 and then 2 to 1. So that's why this rho 1 1 is positive. Similarly, you can check that these are all positive. So from 1 you can go anywhere with positive probability, but still transition probability from 1 to other state is no, sorry, from 1 to 0 is positive, from 1 to 1 also positive, from 1 to 2 is also positive, but from 1 to 3 4 5 they are 0. But still you have put positive, because from 1 to 3 the transition probability is 0, but the two-step transition is not 0. You can go from 1 to 2 and then 2 to 3. Similarly, you can do this for the other state also. It will be all positive. So from 2 leads to every other state, but 3 cannot lead to 1, 2, 3. Just but you can lead to the other, and this is also 0, 0, 0, and this is positive. You can just check with that. You can easily check. This will be the matrix for the row xy. If row xy is 0, then it is 0. If row xy is positive, the corresponding position is plus sign. That means 0 is the absorbing state, and 1 from 1 we can go 0, 1, and 2 everywhere. From 2 you can go everywhere, but from 3 you can go 3, 4, 5. From 4 you can go 3, 4, 5. From 5 you can go 3, 4, 5. That means your 3, 4, 5 is a closed set. 3, 4, 5 is a closed set. 0 is also a closed set. But if you include 1, then there are no trivial closed set, no proper closed set. The whole state is a closed set. Set containing 0 is a closed set. Set containing 3, 4, 5 is a closed set. And set containing 0, 3, 4, 5 is a closed set. And 3, 4, 5 is actually irreducible closed set, because from 3 you can go anywhere in 3, 4, 5. So this is the idea. So 0 is an absorbing state. So it is an irreducible closed set, and it's a recurrent state. Hence, it's a recurrent state, and it is a irreducible closed set. So C1 set containing only 0 is irreducible closed set, and C2, this 3, 4, 5 is also closed, irreducible closed set, and also irreducible. But what about 1, 2? So state 3, 4, 5 and 0 are recurrent. What about 1, 2? 1, 2 is a transient state. You can easily check that 1, 2 is a transient state, because if you start from 1, 2, you ultimately leads to 3, 4, 5 or 0. And if you go to the 3, 0 or 3, 4, you can't back to the 1. So with positive polarity, we land to the one of this closed set, and you can't back in the 1. So 1 is a recurrent transient state. So 1 and 2 both are transient state. Sorry, it's transient state. Now, set of all transient state. What are the set of all transient state? Set of all transient state is also right in notation S suffix capital T is 0, 1, 0, 2. Sorry, set containing 1, 2, and set of all recurrent state is also right. S R for recurrent, T for transient is 0, 3, 4. And what are the irreducible? These are the C1 union C2. And what are the closed sets? The closed set is C1, C2, C1 union C2, and the whole script S, the whole state S. This is closed. No, there's one closed set also. You can take C1 union 1, just 1. That's also a closed set. No, sorry. So if you take 1, then you have to take 0 also, because you can go from 1 to 0. 1 to 2. Oh, right. So this is not the closed. Sorry. So if you take 1, then you have to take 0, 1, 2, both, all 3. So, right. And if you take 1, then you have to take all 6 actually. And if you take 2, then you have to take all 6. So if you include in the closed set 1 or 2, then actually the whole state space 1, 0 set containing 0, 1, 2, 3, 4, 5. This is a one closed set, trivial thing. It is true for every Markov chain. Now, if you just omit, drop your 1 and 2, then there are 2 closed set only, irreducible, set containing 0 and set containing 3, 4, 5, and just their union is also closed set but not irreducible. So there are 4 closed set. Among 4, there are 2 irreducible, and other 2 is not irreducible. So this is the basic idea of for any Markov chain. You just first you have to find this matrix of row xy is either positive or 0. And we'll stop this lecture with a last result, very important, is the theorem. Suppose that the state, this set of all recurrent state of recurrent states is non-empty. So that means at least there is at least one recurrent state is non-empty. Then this set of all recurrent state is the union of A finite or countably infinite. Countably infinite. It cannot be uncountable. So countably infinite number of disjoint irreducible closed sets. So the set of all recurrent state is actually is a closed set of all recurrent state is a closed, because the outside this state, this set, there is all a transient. So why it is closed? Because if any element y is outside this set of all recurrent, then and take any element x in the recurrent state. So x is recurrent, y is transient. But if x leads to y, then y cannot be transient. So if x is recurrent, y is transient. That means x cannot lead to y. So it is a set of all recurrent state is a closed. Now this closed is actually the union of some closed set, irreducible closed set, and actually every closed set is a union of some irreducible closed set. But this is countably many union, can't be uncountable. So the proof is slightly straightforward. It's non-trivial but straightforward. So choose any element from the recurrent state x. So x is recurrent, and C be the set of all states y in recurrent state such that, so we take some part of this C such that x leads to y. So x leads to y. X is leads to y. So to collect all this y, which from x you can go there. So let's see, C is a set. Now since x is recurrent, row xx is 1, and hence what happened? X is in C. So x itself in C. So it's like equivalence relation, x relate to x. Now suppose y in C and y leads to z, then what happened? So y in C means, so y in C, what is the meaning of that? That means x leads to y, and y is again recurrent because x is recurrent. Y is recurrent. Now since x leads to y and y is recurrent, that means x leads to z, because this leading thing, this is a equivalence relation. If x leads to y, y leads to z, then y leads to z, and since y leads to z and y is recurrent, so z is recurrent. That means therefore x z in C. So what is the meaning? Meaning that is this C is a closed set. C is a closed set. So C is closed. Now suppose that y, z in C, two elements are in C, and x is recurrent. Is also y z leads to y z. We have to write this also, because the close means every element of a C leads to every element of y. It's just not x leads to every y. You have to prove all y leads to all z. X is recurrent, and since and x leads to y, because y and z both in C. We assume that, suppose that. Therefore, y leads to z, that we actually write the previous. Therefore, C is irreducible. So every element leads to the every element. So it's irreducible. Now let C and D are two irreducible closed set. So C and D are two irreducible closed subset. So two different subset of this set of all recurrent state. And suppose that there is a common element. So we'll show that it can't be there. So if two close irreducible closed is the two part, it can't have a common element. It should be phi. This makes a partition basically. So suppose x belongs to this C intersection D, we'll show such a x is not exist. Now choose y in C. Now since y in C and x in C and D both, so x leads to y. That means since x leads to y and x in D, and D is a closed set, that means y in D. That means C is a subset of D. And similarly, we can show? Similarly, we can show that in a similar argument, similarly is actually a symmetric idea. So D is a subset of C. So that means C equal to D. So if you take any two irreducible closed set, that must be equal, or it is disjoint. So if any x is not disjoint, any x is there, so it creates a partition basically. So that is either C intersection D is phi, or C equal to D. That means it creates a partition. So it creates a partition, and since it creates a partition, so that means the whole set. Therefore, this has a partition of consists of closed set, irreducible closed set, irreducible closed set. Irreducible closed set. So this is a complete theorem. So I will stop here this part, and next time we discuss with some martingales, and actually the Markov chain is almost done. So we need some other chain like queuing chain. Martingale is not a Markov chain; is a slightly close to Markov chain. Then branching chain, then Bach's and chain. Then we go to the again the stationary distribution of all this chain, and then we derive some null recurring state and positive recurring state. These are there, and some theorems, and then some important result, and we discuss on the irreducible chain the limiting distribution or stationary distribution, and then convergence of this stationary distribution, whether this is a convergent or not. This question is there: is there the stationary distribution, the limiting distribution is there convergent or not? If it is converged, is it converged to the is a stationary distribution or not? This question will be there, and in under what condition we get this. This is the whole thing in the next